In this video, we're going to look at testing hypotheses regarding the difference of two means using a matched pairs design. In other words, we're going to have two dependent samples. So the individuals in one sample determines the individuals in a second sample. So to test hypotheses regarding the mean difference of data obtained from a dependent sample, in other words, we're using matched pairs data, use the following steps provided that the sample is obtained by simple random sampling or the data result from a matched pairs design experiment. So we have to have randomness. The sample data are dependent, matched pairs. So the individuals in the second sample are dependent on the individuals in the first sample. The differences are normally distributed with no outliers, or the sample size n is large. So this is to ensure that we have normality. So we either have to have a large sample, meaning 30 or larger, or if we have a sample smaller than 30, we must verify that they come from a normal population by using a normal probability plot or a QQ plot. The sampled values are independent, which means the sample size can't be more than 5% of the population. So we have to have independence for the individuals within the sample, but sample 1 and sample 2 values are dependent. So step 1, we're going to determine the null and alternative hypotheses. The hypotheses can be structured in one of three ways, where mu sub d is the population mean difference of the matched pairs data. So what we're going to do is we're going to find the differences between each pair of data, and so we're going to use that to test mu sub d. So the null hypothesis will be that mu sub d, so again that stands for mu of the differences, equals 0. So what that means is if mu sub d equals 0, that means there is no difference between the matched pairs of data. So that's going to be our null hypothesis. So then our alternative hypothesis will either be that mu sub d is not equal to 0, which means we'll have a two-tailed test, mu sub d is less than 0, which means we'll have a left-tailed test, or mu sub d is greater than 0, which means we'll have a right-tailed test. So we're saying with the null hypothesis that there is no difference between the two means, whereas in the alternative we're saying there is a difference. Step 2. Select a level of significance alpha depending on the seriousness of making a type 1 error. So again, that's similar to other hypothesis tests that we've done. And then we can use either the classical approach or the p-value approach. So in step 3, compute the test statistic. So our test statistic, T0 in this case, is going to equal d bar. D bar is the mean of the differences. So we're going to take each value from the first sample and subtract the value that's paired with it from the second sample, and that's going to give us D. We're going to do that for each pair and calculate the average, and that's D bar. So T0 is equal to D bar minus 0, which would just be D bar, divided by S sub D, which is the standard deviation of all of these differences, divided by the square root of n. Now whether we're using the classical approach or the p-value approach, either way we're going to calculate that test statistic. And that test statistic is going to follow student's t-distribution with n minus 1 degrees of freedom. The values of d bar and S sub d are the mean and standard deviation of the differenced data. So we're going to use the student's t-table or some other means to determine the critical value if we're using the classical approach. So we're going to figure out the critical values like we've done in other tests. And so if we have a two-tailed test, depending on our level of significance, we'll find the two critical values. If we're using a left-tailed test, we'll have a negative critical value. If we're using a right-tailed test, we'll have a positive critical value. So we'll use either the student's t-table or one of our technologies to figure out what those critical values are. And then step 4, we're going to compare the critical value to the test statistic. Or again, I prefer to say that we're going to compare the test statistic to the critical value. So if our T naught falls to either the left or right of these two critical values in a two-tailed test, then we'll reject the null hypothesis, otherwise we won't. In a left-tailed test, if the test statistic is to the left of this critical value, we'll reject the null hypothesis, otherwise we won't. And in a right-tailed test, if the test statistic is to the right of this critical value, we'll reject the null hypothesis, otherwise we will not. So that's what this is saying, and then we'll state our conclusion. Now, if we're using the p-value approach, again, we're following a student's t-distribution with n-1 degrees of freedom. So the p-value would be, if we have a two-tailed test, then this test statistic's either going to be negative or it's going to be positive. We're going to use it and its opposite. So one of those values will be negative, one will be positive. The area on the outside of the two tails will be the p-value. Now, if we have a left-tailed test, then the p-value will be the area to the left of the test statistic. And if we have a right-tailed test, then the p-value will be the area to the right of the test statistic. And again, if we're doing a two-tailed test, the p-value will be double what it would be if we're doing one of these one-tailed tests. And then, of course, we also have the possibility of using technology to compute the p-value. Regardless of how we figure out the p-value, if the p-value is less than the level of significance alpha, we will reject the null hypothesis. But if the p-value is greater than or equal to alpha, then we will not reject the null hypothesis. And then step 5 will state our conclusion. So this process, you're going to see over and over and over again, we have this same process for conducting a hypothesis test. So let's take a look at an example. Car rentals. The following data represent the daily rental for a compact automobile charged by two car rental companies, Thrifty and Hertz, in 10 locations. Test whether Thrifty is less expensive than Hertz at the 0.1 level of significance. Note, a normal probability plot and box plot of the data indicate that the differences are normally distributed with no outliers. So they've told us this last part in the setup of the problem because we only have 10 pairs of data. And so those sample sizes are less than 30, so we have to verify that the data comes from a normal population because our samples are less than 30. So we have to have that, otherwise we would have to do a QQ plot or a normal probability plot, and we'd have to do a box plot to verify there's no outliers. So we're good with that. We're going to trust that what we're told in the setup of the problem, we don't have to do that. We're supposed to test, is Thrifty less expensive than Hertz? So on average, is the price of Thrifty rental cars cheaper than the price of Hertz rental cars? So if I think of Thrifty as population 1, and if I think of Hertz as population 2, just so that I keep it straight, then I want to know, is population 1 on average less than population 2? But in this case, we have a matched pairs design because we are looking at the rental prices by city. So the fact that we took a Chicago price here meant we had to get a Chicago price here. The fact that we have an LA price here means we had to get an LA price here, and so on. So this is a matched pairs set of data. This is a situation where our sampling method is dependent. So we need to establish a null hypothesis and an alternative hypothesis. So the mean of the differences equals 0. That is our null hypothesis. And the mean of the differences is less than 0 is going to be our alternative hypothesis. And this would indicate that Thrifty is less than Hertz. So if Thrifty is less than Hertz, then that means we're going to get a less than in the differences. And so what the differences would be literally, if I take Thrifty minus Hertz, Thrifty minus Hertz, Thrifty minus Hertz, and so on. That's going to give our differences D. Now I'm going to find those differences, but I'm going to use the calculator to do that. So in my calculator, I have entered the Thrifty data into list 1, and I've entered the Hertz data into list 2. So I'm going to go over to list 3, and I'm going to highlight the L3, and I'm going to type in L1, which is the second of the 1 button, minus L2, which is the second of the 2 button, and press enter, and that finds all of those differences. And I'm going to write those down here. So in Chicago, Thrifty was actually $2.82 more expensive than Hertz. But in LA, Thrifty was $8.10 cheaper. And in Houston, Thrifty was $2.09 cheaper. And in Orlando, Thrifty was $8.01 cheaper. In Boston, Thrifty was 99 cents cheaper. In Seattle, Thrifty was $1.03 cheaper. In Pittsburgh, Thrifty was actually 91 cents more expensive. In Phoenix, Thrifty was 76 cents more expensive. In New Orleans, Thrifty was $6.82 more expensive. And in Minneapolis, Thrifty was $2.50 more expensive. So again, you can see we have lots of positive, lots of negative. The question is there no difference between Thrifty's prices and Hertz prices on average, or is Thrifty cheaper, which means the mean of the differences would be less than 0? So in order to conduct this test, what I'm really doing is I'm testing these differences, more so than testing the individual values. I'm testing the differences. So what I need to do is I need to calculate D bar and I need to calculate S sub D. So I need to calculate the mean of these differences, that'll be D bar, and I need to calculate the standard deviation of these differences, that would be S sub D. Well, I'm going to use my calculator to do that. I have in list 3 those differences. So if I do stat and calc, one variable statistics, for the differences that are in list 3, so if I calculate that, I get, now the calculator says X bar, but this is D bar, that equals negative 0.641, and S sub D, again the calculator calls it S sub X, but that is 4.645079715. So D bar, the mean of the differences in the sample, is negative 0.641, and S sub D is equal to 4.645797715. So I need to calculate my test statistic. Whether I'm using the classical approach or the p-value approach, I need the test statistic. So T naught was equal to D bar divided by S sub D over the square root of N. So in this case, D bar is negative 0.641. S sub D is 4.645797715, and our sample size is 10, so that's divided by the square root of 10. So if I bring back in my calculator, negative 0.641 divided by, I need parenthesis for the denominator, 4.645797715 divided by the square root of 10. Again, that was our sample size. Close the parenthesis for the denominator. And so our test statistic is negative 0.436. So this is approximately negative 0.436. So if I use the classical approach, I need to compare this to the critical value, which I need to determine. Now, in this particular case, we're dealing with a t-distribution. N equals 10, so that means we have 9 degrees of freedom, 10 minus 1. We're dealing with a left-tailed test, so that means alpha is going to be in the left tail, which means we're going to have a negative critical value. So this area right here is 0.1, and I need to figure out what that critical value is. Now, how can I figure out what that critical value is? Well, I can use the student's t-table. I can use inverse t on my calculator if you have an inverse t command on your calculator, or you can use the t calculator in StatCrunch. Any one of those three options will work. Just remember, if you use the table, that this has to be a negative critical value because it's a left-tailed test. Now, I'm going to use the inverse t command. So I'm going to distributions, inverse t. The area in the left tail is 0.1. The degrees of freedom are 9. And so if I paste, I get negative 1.383 as this critical value. Negative 1.383. Now again, zeros here. So if I compare my test statistic to that critical value, the negative 0.436 falls to the right of that critical value, so that tells me do not reject the null hypothesis. Now that was using the classical approach. If I want to use the p-value approach, so using the p-value approach, I need to find the p-value. So the p-value would be the area to the left of the test statistic, which is negative 0.436 in this case. So this area to the left of negative 0.436 in a t-distribution that has 9 degrees of freedom, that would be the p-value. So this right here is the p-value. Now how do I figure that out? Well, I can use the student's t-table. Now with the student's t-table, I won't be able to figure it out precisely, but I can get an approximation of what it would be. Or I can use the tcdf command on the TI calculator, or I can use the t calculator in StatCrunch. Any one of those will give me this p-value. Well, I'm going to use the tcdf command on my calculator. So if I bring in my calculator, I'm going to go to distribution and tcdf. So in this case, we do not have a lower bound, so we're going to need a big negative number. Well, negative 1 times 10 to the 99th is a big negative number. My upper bound is negative 0.436, and I have 9 degrees of freedom. So if I paste, then I get 0.3366 if I round to 4 places. So the p-value is equal to 0.3366. Now that is bigger than 0.10, so again that tells me do not reject the null hypothesis. So based on this data, there is not a difference in the price between Thrifty and Hertz. In other words, Thrifty is not cheaper than Hertz. So to answer the question here, again the question was, is Thrifty less expensive than Hertz? And the answer to that is no. Thrifty is not less expensive. There is not a significant difference in our statistics to say that Thrifty is cheaper. Now we can also conduct this hypothesis test directly using our calculator in StatCrunch, and I'm going to show you that in the next video.